So today we're going to talk about Taylor polynomials and approximations. So in this lesson, we're going to find a process to write a polynomial function that will approximate functions such as sine of x, cosine x, e to the x, and natural log of x. Now these approximations are known as Taylor polynomials. And it tells you right here that in fact, the tangent line approximation, right, when we use linear approximation, I don't know if you remember that from the AB part of this course, that's something like that, right? And that's actually a Taylor approximation of degree 1. Now, there is, and by the way, and this also says that approximates f of x near a, which a represents a constant, an x value. Right now, if a is equal to 0, meaning if we're centered in this approximation around 0, this is called a special case, so we call it Maclaurin polynomial. Now, before, there is a section that I'll probably attach to this where they try to basically construct a Taylor polynomial from scratch, and you can kind of see where the formula came from. And I'm also going to attach a couple of videos from Khan Academy where he does a really good job of explaining where all this stuff comes from, okay? So not to lose time, let's just go on. So the definition of an nth degree Taylor polynomial is what you see right there. And then notice that this f of c, that literally means is a function defined at a specific x value, okay? And then f prime of c, that's sort of what we talked about, is the function, is the derivative of the function derived at the same x value, and so on and so forth, right? Notice that even though we didn't write it, technically we could write this as 1 factorial, which is just 1. And 0 factorial, by definition, is also 1, okay? So you can kind of see how the formula goes. Now, we also, if c is equal to 0, and this is the important part, right? Because a lot of the times they don't actually tell you that c is equal to 0. They just tell you to use the Maclaurin polynomial, all right, to approximate a function. Well, when they do that, they automatically are telling you where the function is going to be centered at, which is 0. Right now, notice that these two functions are very similar, except for now, what they did with this one, all right, is they just plugged in c is equal to 0, as you can tell. And if you plug in c is equal to 0 here, you can kind of see that you're going to get exactly this function, okay? So the Taylor polynomial is actually much more general, okay? And the nth degree Maclaurin polynomial just applies when c is equal to 0. All right, so let's go ahead and move on to example 1. Now, suppose that f is a function that has continuous derivatives, and that's the important part, right? In order for you to do a Taylor polynomial, you have to make sure that you have an infinite amount of derivatives, okay? So you have first, second, third, fourth, fifth, sixth, seventh derivatives, and so on. So in this case, we don't even know what the function is, but we're going to try to use the Taylor polynomial to approximate what this function is, right? So we're going to call this approximation T3 of x, all right? And then remember, we're going to use this formula up here, this one right here, right? F of c just says that in this case, c is 2, right? It's centered around c is equal to 2. So f of 2 is 1, so I'm just going to write a 1 here. Now, notice that the next part of the formula says f prime of c, which is, in our case, is f prime of 2. And for us, f prime of 2 is negative 3. So we have minus 3. And then we have x minus c, which is x minus 2 in this case, to the first power. Okay? Plus, now we have f double prime, and you can see that up here. Well, f double prime of c, which in our case is 5. X minus c, which is x minus 5, minus 2. Squared all over 2 factorial. And then plus, or in this case, plus negative 7. So I'm going to write that as a negative 7. Minus 7x minus 2 to the third power all over 3 factorial. All right, so again, this right here approximates the function that we can't see. Now, most of the time what they're going to do with this is that they're going to ask, sometimes they'll ask you like, approximate using the Taylor function, what is t of 3 is equal to, I don't know, let's say 5. And then this will give an approximate value of what f of 5 would be. Okay, approximately the same. But we'll cover that later. Right, in example 2, we're going to use the formula above to construct a Taylor polynomial that approximates sine of x. Okay, So, and actually, and after I'm done, after I show you the formula, you can feel free to actually plug that on your calculator to see how they match up. All right. Remember, it's an approximation, but it actually does approximate a lot of the values that you're looking for. Okay. So now we're going to use the Taylor polynomial to approximate sine of x. Now, notice that I have already, just to save some time, I've already written all the derivatives here. Okay. And in green, I've written those same derivatives defined at f is equal to 0. Now, because they tell me x is equal to 0, this is a Maclaurin polynomial, all right, which I can use the Taylor series. There's nothing wrong with that, but just to save us time, I'm gonna go ahead and go straight into the nth degree Maclaurin polynomial that you see at the top. So let's call this m5 of x. Now, according to the formula, right, we're going to have f of 0, which is 0. So I'm going to go ahead and write the 0 so we can at least be on the same page here. So we have 0, and then we have plus f prime of x. F prime of 0x, which in our case is going to be 1 times x, which is just going to be x. Okay? And then we have, let's see, plus the second derivative at 0, which in our case is 0 over 2 factorial times x squared. Okay, so at that point I'm right here. And now we have, let's see, minus 1 x cubed. Negative 1 times x cubed is just x cubed over 3 factorial. Let's see what else. The next one's also going to be 0, so we have plus 0 x to the 4th over 4 factorial. And then, what is the 5 here? Plus 1 x to the 5th over 5 factorial. Okay, now obviously I don't have to write the 0, so I can simplify this much easier if I just write it as x minus x cubed so this is the answer right here. Okay, so again, if you were to plug this in into your calculator, it should somewhat simulate what's going on with the actual function, which is sine of x. Okay, now later on we're actually going to write a they're going to ask us to write it, so I'm going to go ahead and write it just because I know what's coming. They're going to ask us to write this like a sum. Okay, now to write it like a sum, and I did have to look this one up because this one's not necessarily the most intuitive. I mean, this part was intuitive, I thought, but then I couldn't get the right signs, so I did have to look this up. So if I wanted to write it like a sum, I would write it like that. Okay. Now let's go on and use the nth degree Maclaurin. Let's write the nth degree Maclaurin polynomial for cosine. All right. So same idea. I went ahead and took several derivatives until I can get basically the idea of what's going on, and we're gonna go from there. All right. So first, we're gonna call this the Maclaurin. I don't know. Let's call this n to the x. I'm just gonna write a few, right? So pretend this is like a not a series, but a sequence. And the first one is 1. The next one is gonna be x squared. So notice that I went from here to here, okay? Because the middle part is 0, so I'm not gonna write it. So you start with the constant, then you have the x value, and then you have the x squared value. And I'm gonna go to this one right here. Well, that's 0, so let me go to that one. So then let's see. I went. This is like 0, 1, 2. Yep. Okay, that makes sense. And this is like 3, 4, 5. Okay. Let's see. Plus x to the 4th in my case over 4 prime. 4 factorial. And notice that even though I didn't write it, you can kind of see that in the next one, I started with a positive, and then a negative, then a positive, then a negative. And that's going to be x to the 6 over 6 factorial. And if I want to write another one, I can write a plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial. And then dot, dot, dot. Let's see if we can figure out what the nth degree Maclaurin polynomial for cosine would be, right? Mainly, you can see that the signs keep switching back and forth, right? If you can see that, then you should understand why I'm writing what I'm about to write. And in this case, 2n represents an even number. Just like here, the 2n plus 1 is an odd number. Okay, so let's go ahead and move on to example 4. All right, so they want us to write some kind of pattern also for the Maclaurin polynomial for e of x. All right, so first write that, and then we're going to take the derivative of that, which is going to be, well, it's the same thing as e to the x times the derivative of the power. The derivative of the power in this case is just 1, so basically it doesn't really matter how many derivatives you take here, you're going to get the same thing. Okay, now, since this is a Maclaurin polynomial, then I know that c is 0, right? So they want this center around 0. Now in this case, for all of these are all going to be 1, right? Because the function is the same. All right, so let's go ahead and write it. All right, so for this, we have the Maclaurin polynomial to approximate e of x. So the first one is 1, and then we have plus x over 1 factorial plus x squared. So basically I have 1, 0, 1, 2. That's what I'm at, okay? This is like 0 factorial, even though we never read that. But, and again, 0 factorial is 1. So this is 2 factorial. And then, if I keep going, I would have like x cubed over 3 factorial and so on and so on. All right. So this one, I think the nth degree Maclaurin would be a lot easier to see, right? Where I can write it as x to the n over n factorial. All right, so you'll be required to memorize the Maclaurin polynomials for the 3 functions that we had just created. So it's important for you to recognize them in their general sigma notation form. All right, so again, I kind of show you where this comes from, but these are the actual summations. So the sine of x alternates in our numbers. All right, for the cosine, oh, sorry, I copied the wrong one. Cosine, I feel like it's a lot easier for me to remember. On even numbers. And then finally we have e to the x. Okay, so let's go ahead and move on. Now there's some technology stuff on here that I'm going to write, but a lot of you are probably not going to have to use this because you need an Inspire or a T89. I will talk about the error thing at least in case you see it or in case there's a question being asked about it. But again, I don't think they would have a question like this on the AP exam, on the BC part at least, because I think they assume that at least some people are using the 84. Okay, so let's say, but the instructions are right here. If you happen to have an Inspire or a T89, and if not, you can just YouTube it like I have. All right, so P of 5, what this means right here is that they're actually using the Maclaurin polynomial, right, to approximate what f of 1.5 would be. So the actual answer would be this. Okay, now the approximate answer is up here. All right, so if you want to know what the error in your approximation is, you would just have to have the actual minus the approximation. You take the absolute value of that. Okay, so same thing on the second one. Okay, so let's see. This would be the approximate. This would be the actual. Now, so it says the error of P of 5 of 2 compared to the error of P of 5 of 1.5. Now, you can tell that, hopefully, that the error on the error is greater. P of 5 of 2 error is greater than P5 of 1.5. Now, let me think about this here. So here's the idea behind it, all right? That the further you get it, now remember, because we're talking about a Maclaurin polynomial, that means that we center this approximation around c is equal to 0, okay? So the reason I'm talking about that is because what would happen if you use the polynomial, they're talking about the Maclaurin polynomial, to estimate 2.5? Well, the further away you get from the center, which in this case is 0, the greater your error will be. Okay, so let me write that down. Oh my gosh, what is that? From the center, which in this case is c is equal to 0, the greater the error will become. Okay. Now they also have some stuff over here called, which is basically the same thing, okay? But they're gonna talk about this in more detail later on, but it's the same thing, right? So in order for the Taylor polynomials, in order for you to use the polynomials effectively, we'll use the Taylor's theorem to estimate the size of the error. The remainder in the theorem is called the Lagrange form of the remainder, or the Lagrange error bound. This gives us a bound for error, but not the exact value of the error. For now, let's think about errors as follows. So let's just think about the errors for now as this. The absolute value of the actual minus the approximation. And then they talk about Taylor's theorem. I don't really know how that plays out into what we do in this homework because I really didn't have to use it. I'm guessing they're trying to get us ready for what's coming later on. So let's go ahead and now worry about that until we see it. And let's answer the following questions, okay? And it even tells you right here. We will explore the errors and accuracy with Taylor's theorem in the last lesson of this unit. So let's not do it for now. All right, so let's take a look at this. All right, so I actually kind of enjoy this. Well, relatively speaking, I'd rather not do this, but I kind of enjoy doing this because I feel like there's not a whole lot of mathematical jargon to deal with. It's just a matter of understanding what's going on, which is very, very similar to what we do in AB calculus, or calculus AB. So now they're asking us that we have this polynomial, all right, given to is a second degree Taylor polynomial. All right, so we know it's a second degree Taylor polynomial, which approximates whatever this function is. Okay. Now it tells us what are the signs of A, B, and C. Notice that A, B, and C are up here. All right. If F has the graph picture on the right, explain your reasoning. All right. So let's think about it for just a second. So what we're gonna think about here is we're gonna talk about this. Remember, what happens, let me erase some of this stuff so I don't get too messy here. Let me write it like this. Maybe I'll write it down here. If we did a Taylor series, right, this came from basically f of 0. This came from f prime of 0. This is basically what we have here. And then this came from f double prime. And I'm writing 0. Oh, well, I guess that's not Maclaurin then. All right, so those are the that's sort of what's going on, right? So let's just understand. Now think about it. Now, if this function right here is crossing the y coordinate right there, that's actually our value at 0. Remember, this is x is equal to 0, right? So it tells me what that tells me right there. Let me write it the way they're going to write it on the homework for you. Is that A, which is equal to f of 0, and I know that f of 0 is a negative value, right? So we can say it's less than 0. So again, so because of that, how do I know that? And it's asking for justification. Well, because the y-intercept is negative. Okay, now let's look at b. Now we know that b is related to the first derivative of the function. Okay, now at the first derivative, what does the derivative tell me? Well, hopefully you already said that it tells me whether a function is decreasing or increasing. But at 0, we can tell that this function is decreasing. Okay, and what do we know about that? Well, if the first derivative, okay, if the first derivative is negative, how do I know that it's negative? Well, because the function is decreasing. Okay, and then finally, let's look at C. Now, on the C value, has to do with the second derivative at 0. Now, the second derivative at 0, what does that tell me? And I hope you said concavity, right? Now, because the second derivative, or excuse me, because this is concave up, that means that the second derivative is positive. And again, I'm writing my justification here. How do I know that C is positive? That's basically what this is saying. C is positive because F is concave up. Okay, I hope that makes sense. Let's go ahead and move on. Let's look at the next one. All right, you do have a problem kind of like this, all right? So make sure you understand what's about to happen. Now again, suppose you have the function f of x is approximated near x is equal to 3 by the third degree Taylor polynomial. And here's your third degree Taylor polynomial. All right, it says find the values of all of these. Now, first, I hope you notice that this one is like basically like x to the 0 power, if you want to look at it like that. And then we should have something here that's to the x power, but we don't. All right, so what happened here is that this term must have been 0, or must be 0. That was a really weird sentence. So again, that must have been 0. All right, or it is 0. There's no other way to do it. All right, so I guess I did all of that just to show you that there's one that's been left out. Okay, now notice that they're asking us for this is a degree 3, and we normally have one more value on there, which gives us the fourth value. So this is 1, 2, 3. So now we have 1, 2, 3, 4. Right. So I know that I'm doing this right. Now let's look at it, right? So f of 3, there's not a whole lot of tricks to it. F of 3 is just 4. We know it. It's just right there, right? Now, f prime of 3, well, the derivative of 3 must have been 0 because that's what I got here. It's not even on there, right? So I'm right because it's not asking to justify, but there you go. There's no x minus 3 to the first power term. All right, now let's see, f double prime of 3. Remember that what happens according to this the formula that we have, right, is that this is normally f prime of 3 is divided by as f double prime of 3 times x minus 3 all over 2 factorial, right? So we can say that all of that gave us all of this gave me a 5. You see what I'm saying? So f prime of 3 over 2 factorial gave me negative 5. So how do I find what f double prime of 3 is? Well, I can do that very easily by multiplying this times 2 factorial, right? So then f double prime of 3 is going to be negative 5 times 2 factorial, which is just negative 10. All right, so there's that term right there. Now let's go on and find, do I need any more terms here? Yeah, we need one more. There's that 6. So same reasoning, f prime of 3 over 3 factorial is equal to 6, right? Because normally all of this is over 3 factorial. Now, because I don't have that, that must mean that this right here was equal to 6. So I'm going to multiply both sides times 3 factorial. All right, 3 factorial is the same thing as 3 times 2 times 1. So that's essentially going to be 6 times 6, which is going to be 36. All right, so those are all the values for all of those. Now, excuse me, that's my alarm. It's 4:20. You know what that means? 5 minutes before the end of class, of course. All right, so let's go on to, my wife is just looking at me like I'm crazy, but she doesn't even know anything I'm saying. I could be making it all up for all she knows. Anyways, moving on. So on this very last one, so does function f have a local maximum or a local minimum? Minimum or neither as at x is equal to 3, right? Now let's think about this briefly, right? What do we know happens at 3? Right? What do we know happens at 3? I'm looking at this very carefully because I know that my first derivative, which is right there, is equal to 0. So what does that tell me? That tells me that I could potentially have a local max, a local min, or neither, right? But I can't just by that number say that I have a local max or min. They could be, right? I need more information. So I know, how do I want to write this? So f prime of 3 is 0. So there could be a max or min or neither, right? Now, what happens in the second derivative? I mean, I know that's what you're asking yourself for sure. Now, according to what we wrote on the previous problem, we know that f double prime of 3 is negative 10. Well, who cares? Well, what do you know? What does the second derivative tell you? It tells you concavity, right? So because negative 10 is negative, then that tells you that you're concave down. And at that same point, the first derivative is 0. So that must mean that you have a local max, okay? So what this is called a second derivative test, right? So to kind of save us some words, because I don't necessarily want you to explain all of that if you're doing the AP exam, what you can say, just to save you some time, is you can write it like this. Well, never mind. I can't find it. There it is. Couldn't find it there for a second. Let's see. I'm going to write the justification right here. F prime of 3 is 0. and that's a very big and, the second derivative is negative. So by the second derivative test, function f has a local minimum at x is equal to 3. A local maximum, excuse me. Okay, so that's that for the notes, guys. Let me see if there's anything to note on the homework that I found particularly difficult. I don't think there was. I think everything's pretty straightforward. So far, this is my favorite unit. All right, there's some writing to be done, but it's not very hard, hopefully. All right, so again, if you guys have any questions, please let me know.